Welcome back to Retro Depot. Today we're taking a look at the third installment of the Digital Logic series. We are going to be taking a look at building a UART. It's going to be a simple one. We don't need anything super fancy. The purpose for doing this is, one, I've never actually designed a UART before, and I don't need anything super fancy for the computer I'm working on. I just wanted to incorporate the serial port into the Max CPLD that we are going to be using for our memory mapper as well as our I/O decoding. So I figured that we would take a look at designing a UART. Now, probably the easiest way to start this project is to take a look at something that's similar in design, and I can't think of anything that would be more similar in design than a shift register. So we're going to be focusing on the transmitter portion of this first, because I think the transmitter is going to be the easiest thing to actually probably design at first, because really all we need to do is be able to shift out bits. So that said, my favorite shift register for parallel to serial output is the 74-165. So we're going to go up here and we're going to take a look at shift registers. And as you can see, we got our 74-165 here. We're going to right click to open up the circuit. And there you go. That is essentially what the insides of a 74-165 look like. Now, this is going to be close, but it's not going to be exact. What we really need to do is we need to make a couple of changes. The first being is that we need to add in an extra stage here, and the purpose for that is so that we have a start bit. We also don't need VCC and ground because that's already connected internally on the CPLD. And we need to change a couple things about the inhibit, as well as getting rid of this serial clock here. We don't need that. We're just going to tie that to ground so that it generates our stop bits for us. And we're going to have to also do some work with our load circuit here, which is going to ultimately be our write pin on the design itself. So let's go ahead and copy this. Control C. And we are going to get out of that window. We're going to get rid of this. We are going to paste this right in here like such. Now we can edit it. So first thing we're going to do is get rid of that. We don't need that. Probably the next thing that we want to do is get rid of this, because we don't need that either. As a matter of fact, we are going to tie that to ground. R to rotate, and we'll just plop that right there. Okay, now we can get rid of these because, again, we don't need those. And I think we're actually going to need 2 additional shift registers. And the reason for having 2 is because we need one for our start bit, and we need to start off with a 0, so we need an extra one there. So let's go ahead and drop one right here. Now we do want to wire these up, and we want to wire it up so that it's pretty similar to the way that the other one is. So let's take our Q input here. We're going to attach that to D. We're going to need a AND gate here. We'll tie that to clear, and we will tie one leg here. We're going to need a NAND gate, and I believe that's about right there. We're trying to keep this as neat and orderly as possible. We need to put in a positive voltage here for the other side of it, because again, we're wanting to make sure that we have a 1, and we're just going to tie that in here. Our set pin is going to come from here, and then our clock is going to be the same clock. Now on the next stage, this one's going to be slightly different. We're going to bring this in here as such, And our Q pin is obviously going to be about the same. Our set pin we can actually tie to, actually let's do this just so that we keep it neat. Our set pin is going to be tied to ground, and we want to go ahead and tie that clear signal back into the circuit. And Q is our output, and we will need a output for that, and that's going to be TX. So now we have the basis for the serial port, and we're going to simulate this real quick. So as you can see, we instantly have an output there, so we need to go ahead and clock that out. Actually, that's not working. Why is that not working? Well, let's take a look at it. So well, let me pause the video and figure this out for just a minute. Okay, I'm back. It was a rookie mistake. On the shift register, well, on the flip-flops internal to the shift register, the set bit was knotted, so this actually should have been connected to VCC. However, we don't need to knot it. We can simply drive it from this. And in reality, we could probably use regular AND gates for this as well, because we don't need to knot that. That doesn't really make any sense. But since we're essentially just copying over a schematic to start with, we don't really need to have anything special here. We can just go ahead and use it as such. But if we raise our clock signal high, we're going to latch data in. Matter of fact, let's put 101. We're going to latch that data in. As you can see, we get a high, a low, a high, our start bit, and then a low. So it starts off at low, and if we cycle the clock once, well, oh, I guess we actually got to raise our bit back. So if we cycle the clock once, we get the start bit, we get the first bit, which is a 1, second bit is a 0, third bit is a 1, and then we get our trailing edge of zeros for the rest of it. And that would continue on, and it would actually put our stop bits in there just simply because it's tied to ground here. Now, we need a way of being able to determine whether or not the host system wants us to pause our transmission or not, which means that we need to do some modifications to our inhibit. So what do we need to do to this? Well, the first thing that we need to take into consideration is if we press inhibit high, then we can't cycle the clock, but we need this to finish transmission in the meantime. We want to make sure that as soon as it's done, though, that we are able to stop the system from sending anything else. So first thing that we probably should do is we should probably figure out a way to determine whether or not any of these bits are high. And just like in the IO decoder video, this is probably going to be the easiest way to do this. So what we want to do is we have 9, 10, 10 inputs here, so we're going to OR all these signals together to come up with a way of measuring whether or not we have anything that's still latched in there. So let's just connect all these up. Won't take us but just a moment. Zoom out a little bit so that you can see. Now, if we end up getting a high on any of these signals here, then we will not be able to stop the clock. The clock will continue. Because what we are going to do is we are now going to use a AND gate. As a matter of fact, I can just copy this one. But because this is going to be a low, and we want to make sure that, well, let me see my math here. We want to make sure that CTS is high, because CTS being high is what's going to tell us that that we're fine to transmit. So how would we do that? I guess we need 2 knots, because if CTS is low and, well, let me see here. We'll have to play with this for just a minute. I'm trying to do the logic in my head. But I think, no, I think we just need 1 of these knotted. Let's test out this theory. So we can actually just stick that right there. We can bring this first signal up here, and then let's move that up so that we can bring this in. So let's test out this theory. So raise both of those, and let's set a couple bits here. We'll latch it in. We're beginning to clock the data out, so let's go ahead and yeah, that's low right there, so we're still able to clock. So if it's low, we actually want to be able to stop the clock. So what we're going to do is we're going to knot this. This is the fun with designing live, is you guys get to see all the little thought processes I go through. So raise both of those signals. Let's put some data on the bus. Let's raise this as well, because if it's raised, we want to be able to transmit. So we're going to latch the data in. Yep, and now we're able to clock out data. And then should we latch it in and we're in the middle of transmitting and we drop the signal, we will still be able to clock. But once we get past that last high bit and the rest are zeros, it's going to inhibit that clock from moving, and that's going to essentially tell us that we are not able to transmit any further data. Now, having said that, we can actually use this as a flag as well to tell us that we are in a halt mode, so that we don't write data to it. So let's call this let's just call it INH, inhibit. And let's actually knot this. So component, a knot, we'll stick it right there, and we're just going to bring it up and over. So now let's load some data in there. Latch it in, transmitting, we'll drop. Now it's telling us that we've inhibited the system. We can read this on a status port if we'd like. It's really up to us how we do that, But now we have a way of being able to determine whether or not the host system wants us to transmit or not. And it looks like we have built our transmitter, because now we are able to transmit data. So now let's clear off the screen, and I'll be back and we'll take a look at building a receiver. Okay, so much like the transmitter, we are going to base our design on something that's already built for us. So my favorite serial to parallel shift register is the 74595, as I'm sure it is the same for most of you. So let's take a look at the inside of this schematic. Whoa, blew way out there. Okay, so this is very similar. We got a bunch of shift registers. It looks like they're going into a merger wire here, which is coming out to, I think that's going, yeah, that's a 8-bit register there. So we can get rid of a lot of this. We can simplify it down. As you can see, we've got a tri-state output here. We won't need that, because we will do that once we put all of our bits and pieces together, so that we can gate this as we would like to. That, and we're going to get errors if we try to compile with outputs connected together. We don't need VCC, so we can slim this down quite a bit. So let's actually just take this section here and let's just copy it. So let's get out of here. Let's get out of this. Let's drop our schematic here, and let's take a look at how we want to hook this up. Now, first thing that we want to do is get rid of that, because we don't need any of that. And as a matter of fact, I understand how this is put together, and I really don't like any of it, so we're just going to start over from scratch. We'll leave it there for reference for now. So let's drop in a bunch of shift registers. We want these to be inverted on the set bit though, so that we keep it very similar to what we got before. And we actually need 9, because we are going to, let's just go ahead and get rid of that. We need 9 because we have to capture that start bit as well. So probably the first thing that we want to do is we want to go ahead and tie some of these to VCC, so that we don't have to bother with them. And let's just go ahead and put that there. There we go. We can just tie all of our set bits to VCC. And that'll be simple for us to do to start this thing off. Okay, and probably the next thing that we want to do is we want to, I think we want to hook up our clocks. So let's put an input here, and we can tie our clock lines up to it. This little guy is right in the way. I'd like to keep this as tight as possible. And we will come over here, and we will just connect the dots. Okay, now we need to obviously bring our data in from each previous stage. So let's go ahead and get all those hooked up. Okay, now we're starting to get somewhere. Clear signals. Now we are going to want to erase the data in the shift register upon completion of a received byte. So we're not going to tie this to anything yet, because we're going to have to come up with some black magic here for making this all work as intended. But I think that we should be able to make it work. Okay, now the next thing that we would want to do is we probably want to have a way of telling the system that we are okay to transmit data. How do we do that? Well, probably the easiest way would be with a... You know what? I'm not sure that we need to do that way. What we can actually do is we can bring in a flip-flop. And what we will do is we will tie the reset line to Q. We will tie the read line. There's our IO. Because let's go ahead and get this put together here real quick. Actually, let's we probably also want to knot that, so we will go ahead and bring that in. We are going to use that to drive our set pin, and we will need an output, and we will call this RTS. Now that should give us enough to at least try to test this out, but we will need to tie this off so that we can test without getting errors. So now let's test this out, and we're getting an error. Okay, D. Let's throw an input in. There we go. Alright, so now actually that should be write, not read. Let's fix it. Okay, so now if we clock that data in, now we are getting our bits that are cascading on down the line, and once it gets to the end, it did not set it. I think what we may need to do is flip this around. Maybe this will work better. And there it goes. It flipped the bit. So that's the basis, and when we read, it should flip that bit back up. And it does. But it still drops it low. That's because we are going to need to come up with some way of clearing this. So I'm going to think about this for just a moment, and we will be right back. Okay, I'm back, and I think I come up with a solution. So what we are going to want to use is going to be a AND gate. So we're going to move these out of the way slightly, and we are going to get rid of that because we are going to sit this right there. And the first thing that we want to do is we want a bit that is going to be knotted on the input, And we are actually just going to tie that to clock. And now we are going to take the output of the transmitter, or I guess the receiver, and we are going to tie that right in. Now, what should happen when we are getting data is once that start bit comes on over and is output in the final stage here, it's going to flip the RTS bit and it's going to set this line high. Now the clock pin at that stage will be high, but on the next half clock cycle that will allow it to actually clear this data. And what we can use is we can use this signal here in order to latch the data into a data register. So I think that's going to be the best way to do it. Let's build that up real quick. Actually, let's just copy these. And let me see here. How do I position these so that they're not taking up too much room? Let's drop it down here. Now, I told you that we were going to be doing some black magic here. We actually only need 8. We don't need 7. But we're going to take the outputs and we are going to run them down to the inputs here. And this is going to give us our data register so that we, what did I do? I'm all over the place here. This is going to give us our data register so that we can store the data after the shift register is cleared out. So it's actually a pretty neat way of doing this. Like I said, I've never built a UART before. I've thought about it many times, but I've never actually done it. I keep wanting to stick it down lower, but I'm trying to keep this as tight as possible so that I've got some room to work. We're almost done here, at least with this portion of it. Okay, so now what we can do is we can use this signal here as the clock. And then we want to tie these to high, so let's get a high voltage here, or not really a high voltage, but a logic level 1. We're going to pull this over, probably have to tie it in like that. I think that's probably going to be the best way. Okay, now we want to go ahead and tie these together for now. We're going to have to do something with those as well, be able to clear them out when we read the data. We'll figure that part out here in just a bit though. May have to sit on it for a few more minutes. And let's go ahead and tie that to ground for now so that we can test this circuit out. We're just going to drop some lines down here so that we can visually see what's happening and whether or not our data is performing the way we want it to. I hope you like this software. At first I didn't really care for it too much. I thought it was a little bit difficult to use, but once you learn the quirks, it's actually pretty fun. Okay, so now we can simulate this. I'm going to bring read high. We're going to bring our clock high, or our data bit high, and we're going to shift in. Let's do 3 1s and then the rest zeros. 1, 2, 3. So we got our 3 bits there. Drop that back down to 0. Let's shift this across till it's in that final stage. Now it's in the next to last stage here. When it shifts over into the output, it should flip the RTS bit. At the same time, it should latch the data into these shift registers, and then on the downstroke of the clock, it should reset the shift register itself, and the data will be left in the data register. So let's try that. Down, up, resets the bit. It's latched those 2 bits here, and then on the downstroke, it's cleared out the register, and we still have the RTS bit set, but if we read, it flips it back up, and of course we'll have an output enabled so that we can read the data. So that worked. We have exactly what we need as far as getting this thing running. Now we just need to do a little bit of work. We need a way of being able to clear the data in the data register once it's been read, and maybe a little bit more. I'm going to think on it for a few more minutes, and I'll be right back. Okay, I'm back, and I've got a solution. So again, we need to clear out this data once we've actually read the information from the data register. And I got to thinking about how you could do that, and I actually came up with a pretty neat little idea. So we need to do 2 things. First off, we need to add in a way of clearing this data out, and secondly, we need some way of propagating the data onto the data bus. Now, there's several ways that you could go about doing this, but the easiest, I think, is actually going to be to use another flip-flop. So we're going to copy that, and we are going to stick it right here. We are going to get rid of this because we no longer need to keep that low. The first thing that we want to do is to bring this down here. As such, we're going to connect the clears up, and then we are going to connect up the Q output to it. Now, as far as the rest of this is concerned, we are setting this up as basically a inverting flip-flop. It's just same circuit you would use as a clock divider to essentially change the state of this. Now, we do need to connect the set pin to VCC, so we'll go ahead and pull that over here and connect it up like so. And then for the clock pin, we are going to connect that to the read input. And the next thing that we are going to do is we are going to put some outputs down here. Get this done real fast. Okay, actually, let's go ahead and move this down just a bit because we need to do something else. We need to have a way to propagate the data onto the bus, but not when we don't want it there. So we are going to use an AND gate. And this is all going to make sense in just a moment. Now, the other input to the AND gate, we are actually going to use the knotted input from the read signal. We'll get these connected up and we will be ready to test this out. Oops. And just about there. Okay, so in theory, the way this is going to work is that, and let me make sure I've got my ducks in a row here. I don't want to mess this up. So the way this works is that when we clock data in, obviously it's going to go through the same process. Once the start bit gets here, it flips the RTS bit, it latches the data into the data register, and then on the down clock of the clock, it's going to clear the shift register so that we don't have any more data coming across and doing anything with our shift registers down here that are acting as our data register. Now, obviously, it resets the RTS bit so that we no longer get that signal. And when we lower read, that's going to essentially do a downward clock on this register here, which won't do anything. It will, on the other hand, turn this signal high, which this, along with a high from one of the flip-flops within the data register, will put a high output on the particular data pin that we're looking at. The other one will be a low. Now we're going to tri-state these once we actually get into Quartus, but for now that will allow us to only show highs where we need to, and the rest of it's going to be low. Now, once that read signal goes high after the data has been read, it will effectively clock this flip-flop. And since we have the NOT output going into the D input, that's going to shift it so that it goes to a high state, which is going to clear the data register as well as the flip-flop itself, resetting it back to a 0, and therefore we will not have any data within that flip-flop. And of course, we're relying on propagation delays. Within FPGAs and CPLDs, you don't have as much, but functionally they still act about the same. So that said, with the way that we have it set up now, we now essentially have a fully functioning serial receiver. So we're going to simulate this. So we are going to bring read high, we are going to bring our clock high, and we are going to bring RX high for a couple shifts there. Let's do 3 again. So 1, 2, 3. So now we have bit 3, bit 2, and bit 1. This is our start bit here, and we're going to go ahead and cycle it down the system. Now it's in this last stage before it propagates, so downwards and up, flips that bit. Now it's also latched that data into the data register, so we see we have 1, 2 bits that are high, and then the rest are zeros. Now we can continue to clock that data in. It's not going to do anything, and at this point, if we were to select the read, we get our data on the data bits, and then as you can see, the clock line is low and the Q output is high here. So once it clocks in, the Q output, or I'm sorry, the not Q output is high. Once we clock high, that Q output is going to shift to a high, which is going to clear this data out as well as reset this register. We'll demonstrate that now. So now those 2 data bits, as you can see on these lines, they're low. Our Q output is back to a low. It was just a high for a very short moment. And now we have completely reset the system as well as our RTS bit. So we are absolutely good. Now we can take this and let's stop that. We can take this and move it back up here with the rest of our schematic. Try to line that back up somewhat correctly. And we've got one more thing to do. We need to get rid of this signal, and the reason is because we want to make sure we can only write data when we have a valid start bit there. So we are going to use an OR gate. Do this, and we do want to not one input. since we're going to be dealing with that. And we're going to, let's actually move that up. We're going to connect that back up. And that should allow us to simulate a clock that is unable to, well, an inhibit signal that prevents us from writing data. Actually, we want that high. So we're able to clock that data in, and if we press right, we do get a change. We'll have to figure this out. Give me just a minute. Actually, after thinking about it for just a minute, I'm not incorrect. I actually just had my bit set incorrectly, so whenever it's high, that's when we're allowed to actually send data. So we should still be able to clock that data at that time. However, it's when CTS drops on the TTL level that we're no longer able to clock data into the shift register. We're still able to send zeros or whatever bits are in there, but we're not allowed to write new data. So I was actually correct to my first assumption, which means that we now have everything that we need in order to have a fully functioning UART. It's going to have a buffer of exactly 1 byte. There is nothing else that it can hold, so it's not like we have a 16 byte first in first out FIFO. We do need to go ahead and get rid of this clock signal because we don't need 2 clocks. I've never really understood why a system would have separate clock inputs for both the receiver and transmitter. It doesn't make sense from a logical standpoint because if you're communicating with another system, chances are it's going to be sending the same frequency that you are because it's receiving the same frequency as you are. So it doesn't really make any sense. Now that said, we're done. I'm not seeing anything else that we need to do with this circuit. We've used up, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 10. So that's, what is that? 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. About 29, let's call it 30 flip-flops. So I was right on the money there. Yeah. We have used up 30 flip-flops. That's in addition to the approximately 60 that we used before, so that should stick us around 90 flip-flops in use out of 128. Like I said, we have not used all the combinational logic that we have available to us, so we have plenty of that available. So yeah, I think that we're going to be able to fit probably a clock divider into this as well. I'm not certain what clock frequency we want to use. I'm shooting for 9600 baud with this system because it's going to be, normally I would do like 115k baud, but I think with it only having a single byte that it can store, that we probably want to slow it down significantly so that our system has enough time to read the data. So we've got a couple options here. If I want to do 9600 baud, let's do the math. If we do a clock divided by 64, that's 614.4 kilohertz. But I think if we do by 96, no, maybe 128, I think that will probably get us closer to a given clock frequency. Let's see here. Actually, I know if we do it by 256, that gives us, hold on, 2.4576 megahertz, which that is a standard clock frequency or crystal frequency. A little bit harder to find in my neck of the woods, but I might be able to make that happen. So, in order to divide by 256, I think that we are going to need, is it 8 bits? Yeah, it's going to be 8 flip-flops. We are going to have about 30 available, give or take. So yeah, I think that we should be able to do that now. And as a matter of fact, let's go ahead and do that. So let's take... As a matter of fact, I'm going to pause the video and we're going to get this set up. Okay, I'm back. I've got it all built. I actually relocated it here in the center just simply so that it's not crossing over these data lines, but we're going to simulate this real quick. I've got this clock input set up for a frequency of 256, which means that we should get a frequency of 1 hertz on the outside. So in other words, every second we should get up and down. And if we simulate this, we see we get basically about 500 milliseconds of up, 500 milliseconds of down. So yeah, works just fine. That's our divide by 256. If we hook up a clock crystal of 2.4576 megahertz, that should give us a baud rate of 96 baud. So, or 9600 baud, so that will be slow enough for us to be able to get the data and actually read it. We've got everything else hooked up here, so now what we really need to do is get rid of this guy. We don't need him anymore. We're going to use a input. Here we go. We're going to name that clock. We don't need this guy up here. And we don't need the output there. What we are going to do is we're going to take this and we are going to feed it into what was our clock state right there. And as a matter of fact, let's go ahead and remove this for just a moment. We'll give this a clock of 256 real quick, and we'll simulate. So as you can see, we are getting clock signal up here and then clock signal down there, so everything's working out just the way we want it to. So if we were to write some data onto the data bus and we latch it in, we're going to see it shift out there. And as you can see, we're getting that shift out. And there we go, there's the end of it. And if we do basically the same thing here, we can shift data in. And when it gets here, we're going to get it clocked out. It latches in. Of course, we have our read pin set low, but we shifted that data out. And upon resetting it, our RTS bit comes back. We can actually shift some more data in here. I think that's probably enough. It'll pop it out. It's going to reset the RTS. Once it gets to the end, there it goes. And if we click read, we get that data on the bus, and it resets when we do it. So, yep, we've built a fully functional serial port. Or I'm assuming it's fully functional at this point. I think I got the RTS and CTS values correct. I think that in TTL they're high for it's okay to send me data. It's low if it's not okay to send me data. So that's it. I hope you liked the video. Again, I'm going to be uploading this code to the website. We're going to have another video where we stick all this together and come up with a complete package for loading into a CPLD or FPGA that you can, if you're planning on doing it with an FPGA, you could even take this, load it up with a Z80 core, and at that point have kind of a standalone processor with a decoding scheme and all your I/O on the inside of it, and have it hooked up to 3.3 volt memory. That might be kind of fun. Have a little 3-chip, because literally you would only need the FPGA, a RAM, and a ROM, So you could literally have a little 3-chip Z80 system with all your other stuff internal to it. Of course, that's nothing new. Grant Searle did something similar to that, but kind of a cool concept. You could actually build it all with digital. This is by this guy. Where's his name? H. Neiman. And of course, you can go to GitHub and get this. When you search for it, search Neiman Digital GitHub, and it'll pull you up the information that you need. It's not that hard to find. I'll actually stick a link below, that way you have it, or I hope I remember to. But anyways, I'm glad you were here for the entire video. If you made it this long, I hope you enjoyed it. I hope that you learned a little bit more about how to build neat little peripherals like this. I hope you learned a little bit about digital, because it's actually a really useful tool for simulation and trying to figure out how you're going to build circuits. You know, I had to stop the video a couple times to think about it, but I was able to simulate everything live, and you've been here with me for, you know, pretty much the entire creative process and coming up with this very simple UART. There's not a lot to it. And I said we were done a minute ago, and I turned around and decided to throw in a clock divider. That way we could take in that 2.4 megahertz clock and divide it down to 9600 baud. So, you know, I mean, it is what it is. You know, if you want to try your luck at trying to run this faster, you could always hook it up to something like a 1.8432 megahertz clock, and at that point I think you would get, is it 57600 baud, 56700 baud, something like that. So I mean, you could hook it up, you could run it faster, you could even divide the clock down by less. You can come up with your own circuit. It's not that hard to duplicate this, so you know, it's kind of fun. You know, play with it, build your own FPGAs, build your own CPLDs for integration, or in case like I'm doing, kind of an ASIC. Yeah, it would be a lot of fun to see people start using stuff like this with FPGAs. And I know that they do, but a lot of people write in VHDL. In VHDL, it does have its advantages. It's faster, but at the end of the day, if you're a hardware guy like me and you're not a software guy, you like to build things. And if you, and of course I'll show you this, you know, I've got a whole little thing of little custom chips that I've done here. And, you know, you've got other stuff, you know, I've got some G80 stuff here, MSX stuff that I've been playing with. You know, I mean, there's lots of things that you can do with this. You can build up your little fundamental blocks, and then you can piece them all together and create whole systems. So it's a lot of fun. At first, like I said, I didn't think I would like this software, because it was a little bit difficult for me to learn at first, because I've never played with anything like this. But after I played with it for probably, I would say, I don't know, maybe a week or two, I actually kind of started to like it. And it's a lot easier to use than Quartus. And of course I can simulate within this. And it exports to VHDL. You can even export to Verilog. You can come here, where's it at? Export. Export to VHDL or Verilog. And you can then turn around and use that as a, you know, block in a, you know, larger system. So anyhow, like I said, I hope you enjoyed the video. Subscribe if you haven't already done it and you want to catch more videos like this. If you did like this video, please leave me a like. I know that it doesn't do a whole lot for you, but it does help others find my channel, because the way YouTube algorithms work, if you like it and somebody else has similar interest to you, it's going to pop up in their feed, and this lets them have the opportunity to discover my channel as well and see things like this that they may be interested in. So again, if you like the video, please, by all means, like the video. Just press that thumbs up. Check out the website. Like I said, I'm going to be uploading the code. I'm going to have some links there and a short little write-up on it. It's not going to be anything as detailed as the video itself, but kind of an idea as far as what there might be in the video. And then last but not least, check back next week, because we are going to be going through the next process of trying to stick all this stuff together inside of one package. That way we can bring it into Quartus and upload it. That's kind of the point, and we may end up doing a follow-up video to this as well once we actually get it onto a board so that we can test it and play with it. So again, check back next week and we'll see you then.